Okay, everyone, good afternoon. This is our last lecture and our last week of labs. Any issues with the lab? Most of you finished with lab 4, hopefully. Okay. Okay, I think you have till the end of the week to finish. Yep. And then we have our final exam next Monday at 4 to 6. 4 to 6 p.m. Okay. So today I'm going to finish the CMOS lecture, and then I will run through a quick review for the final exam. Okay. So last time we were talking about transistor level logic. We talked about voltage levels and noise margin. And the idea here was that CMOS gates are able to clean up signals a little bit as they go from the input to gates to the output. And so, this allows there to be a difference between the levels on the output versus the levels on the input. And this gives way to noise margins. We talked about how to calculate that. Then we got into semiconductors. I talked about silicon, which has 4 valence electrons, and it forms covalent bonds with 4 of its neighbors to create this lattice. And then you can introduce dopants in that lattice with either a extra electron that can move through the lattice, becomes a charge carrier, or a hole, which is a lack of an electron. Either way, it becomes the electron or the hole becomes mobile and carries charge, carries current, changes the conductivity of the semiconductor. And so a p-type silicon is when you put holes in there, which would be dopant from column 3. N-type is when you have electrons as charge carriers, and that would be a dopant from column 5. And you can create a diode by putting p-type and n-type silicon together. And if you have a positive voltage on the p-type with respect to the n-type, it becomes forward biased, which attracts the electrons to the junction here between the two. And the holes become also move toward that junction, and you can then send current through the diode. And so a MOSFET is built with diodes. You have a substrate, and then you have these diffusion areas. So the substrate is usually p-type, weakly p-type, so it's p. And then the diffusion areas, which are these little islands, are N+, heavily N doped. And so you basically just get diodes here, right? And then in between the two diffusion areas is the channel. And that's where you want to attract the minority carriers up from the bulk or the substrate to allow conduction between the two diffusion areas, which are the source and drain terminals. Okay? So you want that channel to be as small as possible, the length to be as small as possible. So generally this is going to be your minimum feature size. The smallest, kind of closest you can make two things together. And then this is an NMOS because the transistor is named after the diffusion areas. In this case, the diffusion areas are N, okay? And so in this case, P would be grounded, the substrate would be grounded, which would mean that there was no way to have a higher voltage, to have a positive voltage in the substrate as compared to the or in reference to the diffusion areas, meaning that you create a reverse bias diode between the substrate and the diffusion areas, which means that these guys are electrically not connected, right? So you're not going to have any leakage from the diffusion areas, no current leakage from the diffusion areas down into the substrate. I mean, that's possible, but if it happens, it's a catastrophe. It's a phenomenon called latch up, right? You don't want that to happen. But what it does create is a capacitor, though, because there's no charge carriers at the junction between the diffusion areas and the substrate, there's no conduction, there's no current from the diffusion down into the substrate, but you do get a capacitor. And that has implications for the performance of these transistors. So then you have a gate, and the gate is separated from the channel by a glass, silicon dioxide, which is a insulator. And so you end up with a capacitor here between the gate and the substrate. Okay? So if you put, in this case, a voltage on the gate, it'll draw minority carriers out of the substrate into the channel. Now this is the part that's a little weird, because I told you that P-type silicon has holes, right? Those are the majority carriers. But when you create this capacitive effect, when you put a charge on this capacitor between the gate and the channel, you attract the minority carriers, which are the electrons, right? Which is kind of counterintuitive, right? So there's majority carriers or holes, but there's minority carriers that are electrons. And so you can attract minority carriers in the gate, and then basically what happens is this kind of turns into a switch in a way, where it'll make an electrical connection between the source and drain when that happens, right? So this ends up becoming like a switch. So basically the gate, you put a voltage on there, some voltage above the threshold voltage. It has to be high enough, usually around 700 millivolts. You put a 700 millivolt or higher on that gate, and it'll basically turn on the transistor, right? And so it'll have an on resistance, which is ideally as low as possible, right? And then if the gate doesn't have a voltage on it above the threshold, then the transistor's off, in which case you have the off resistance, which is very, very high. High as possible, because the higher that off resistance is, the lower your leakage current is, right? Make sense? Okay, so that's the way they work. There's also, so that's the NMOS is what I just described, and then the PMOS is just, it operates in reverse. So a PMOS transistor has, it works in the opposite way, where you basically ground the gate and it turns on the transistor. So symbolically, there's this little bubble here. You see that little bubble on the PMOS? That bubble is a logical, like not, active low, right? So you put a 0 on the gate, turns on the PMOS. You put a 1 on the gate, turns on the NMOS, right? And then to build CMOS gates out of this, use PMOS transistors as the pull-up network and NMOS transistors as the pull-down network. So the PMOSs are responsible for driving the output of the gate to 1. And the NMOSs are responsible for driving the output of the gate to 0. Now you might say, well, how do you know for sure that, like, what happens if they're both turned on? What happens if both networks are both on? Well, that's a problem. That would be real bad. You wouldn't want that to happen, because then you just short circuit your chip. So these pull-up network and pull-down network are mutually exclusive because they're complementary in a logic sense, right? So whenever you put inputs on the gate, you're guaranteed that only the pull-up network or the pull-down network will be turned on, right? And you're also guaranteed that exactly one of them will be turned on. Does that make sense? So you might say, well, how do you guarantee that? Well, it's basically just, it comes down to series and parallel connections of the transistors in those networks. That's really what it comes down to. Okay, so in the case of an inverter, it's very simple. There's basically just one transistor in the pull-up network and one transistor in the pull-down network. Remember, the pull-ups are always PMOS and the pull-downs are always NMOS. Okay? Now, why is that, by the way? Why is that? Well, remember that the PMOSs are a 0. You put a 0 to turn them on. But in reality, that's just digital. 0 is digital. What's happening in the analog space actually is, what you're really doing with these PMOS is putting a negative threshold voltage, right? And the reason it's negative is that the reference of the channel is VDD, right? So when you put a 0 on this PMOS, you're actually putting a -1 on there, right? But logically, it's a 0. So anyway, that's the reason why you need to have PMOSs as your pull up, because you have to reference the gate to VDD, right, in order to get a negative threshold voltage on there. Okay, so digitally, again, it's 0 turns on the PMOS. Analog, it's actually some voltage less than negative threshold voltage, negative 700 millivolts, right? Okay, so anyway, yeah, so PMOS is pull up, NMOS is pull down. So because they turn on in opposite logical conditions, right? PMOS turns on with a 0, NMOS turns on with a 1. You know that only one of these transistors can be on, and exactly one will be on at any time. And so you'll either be pulling up or pulling down. When I say pull up or pull down, really that's just a fancy way of saying you're taking the output, which is connected to the middle point on these two gates, and you're using the gate to short the output to VDD, or using the gate to short the output to ground, right? And that's basically how that works. Now, if you want to build multi-input gates like a NAND gate, then it's a little bit more complicated, because then you have to start creating serial and parallel connections of these transistors. So in the case of a NAND gate, you have two PMOSs in parallel, comprising the pull-up network, and two series connected NMOSs in the pull-down, which means if you put 1 and 1 on A and B, then it'll close both of these switches. It'll turn on both of these NMOSs, and they both have to be turned on in order to pull the output down. Meanwhile, neither one of the pull-ups will be on, right? However, if you have 0, 0, 0, 1, or 1, 0, then you'll only be turning on one of the two NMOSs, which will not be enough to pull it down, and you'll be turning on either or both of the PMOSs, right? Now, the problem with CMOS is that, as I mentioned, in order to pull the output up to 1, you have to have at least one input has to be a 0, right? At least one of the NMOSs has to be turned on in order to get a 1 as your output. And likewise, at least one of the NMOSs has to be turned on to pull the output low, which means that if you look at a truth table, all of the rows of the truth table that have a 1 as the output have to have at least one of the inputs as 0. And all the rows that have a 0 output have to have at least one of the inputs a 1, right? Which means you can't make an AND or an OR gate, you can only make a NAND or a NOR gate. So it's like negative logic. Okay, and then so we talked about that, and that was an example of that. We talked about transmission gates, and then we got into power consumption. So dynamic power consumption is basically you're charging capacitors. You're charging and discharging capacitors in general, right? That's what but the dynamic power consumption is the cost of charging the capacitors. Or you could also think of it as discharging, right? Because either way, whenever you go from a logical 1 to 0, you're taking all that charge and you're just dumping it, right? You charge up a capacitor and then you're like, all right, goodbye, and you discharge it to ground, right? Kind of a waste, right? That's why people I mentioned for a long time, one of the open problems is coming up with a way to recycle the charge, right? That would be huge, right? But at the moment, that technology has not become practical yet. So that's the reason why there's this 1/2. So the dynamic power consumption is 1/2. C is the total capacitance, VDD, because the energy required to charge a capacitor is CVD squared, or CV squared. And then the half is because you're only actually, costing power to charge, right, or to discharge, right? And then frequency is how often you do that. So 1/2 CV squared F. Okay, make sure you remember that. Static power consumption is power that's constantly being consumed even when there's no switching behavior, and that's just the quiescent current IVDD, which is leaking down from the power supply through the pull-up network and through the pull-down network, right? Coming all the way through, right? Now you might say, well, wait a minute. Wait a second. I thought when the transistor is off, it's like disconnected. Not entirely disconnected. It's got like, a really high resistance, like 10 mega ohms. But when you have billions and billions of them in parallel, right? You have billions of resistors that are all tens of mega ohms, but they're all in parallel. The equivalent resistance is not so high, right? And so as you scale up the size of your chip, the static power consumption becomes more of an issue. Okay, then we start talking about logic delay. So this is revisiting a topic that we've already talked about. We've already talked about propagation and contamination delay. I mentioned in that lecture, though, that sometimes rising and falling, like when you pull up versus when you pull down, can experience different delays. So in this case, we've kind of further broken down the propagation and contamination delay into rising propagation delay, falling propagation delay, rising contamination delay, falling contamination delay. So it's the same concept that we've already talked about in the timing analysis lecture. The only difference now is that we're separating these out into two categories. What's the delay when the output is being pulled up, and what's the delay when the output's being pulled down, right? Okay, so I mentioned this, that we've got these reverse biased diodes that form between the diffusion areas and the substrate, right? Now, what are the diffusion areas exactly with respect to a logic gate? Well, that's basically your output, right? The diffusion areas are the source and drain terminals, which are essentially the logic gate output. That's how the logic gate outputs, right? And then, of course, the input to the logic gate is the gate, right? That's the gate. That's this thing up here. Okay? So I already told you that the gate is a capacitor because it's supposed to be a capacitor. That's how MOSFETs work. They're fundamentally based on the field effect, the electric field that's formed by charging the capacitor that's formed between the gate and the channel, right? Okay, so it's great that they have a capacitor on the gate because otherwise they wouldn't work, but it's bad because capacitors are slow to charge and discharge. And this kind of works against us. But at the same time, the diffusion areas, which is the output of the gate, they're also capacitors because a reverse bias diode is also a capacitor. So now we get a double whammy here. We get a capacitance on the input of the gate, and we get a capacitance on the output of the gate. And if you connect the output of one gate to the input of another gate, you got the capacitance of the diffusion area added to the capacitance of the gate on the downstream, on the successor gate, right? The guy you're driving, right? That's real bad. And that's what causes chips to be slow. Okay. Also, and I didn't mention this last time, but this is important. I mentioned that the channel is your minimum feature size. Why? Because the rate at which you can turn on a transistor not only depends on the capacitance, which of course is minimal when the plates of the capacitor are smallest, right? Right. But the charge carriers, the minority charge carriers that are attracted out of the substrate and come into the channel, right? They have to move. They physically move. Those electrons and holes physically have to move. And they don't move at the speed of light. They move actually a lot slower than that. That's referred to as the mobility, the carrier mobility. Okay? So by making the channel length, in other words, the distance between the source and drain, or the distance between the diffusion areas, as small as possible, the transistor will switch faster because the carriers can get across that channel faster if they have less distance to cover, right? However, the width of the channel, now remember, these are two-dimensional. Everything I've shown you so far is a cross-section, right? Like cutting a sandwich. But remember, these these structures or chips are two-dimensional. If you look at the other dimension, you have the width of the channel. So the length is what we've been looking at. So when Intel says, we have a 4 nanometer process, that's the channel width, 4 nanometers, right? But the width is usually about 10 times the length at a minimum, right? But if you make the width even longer than that, than 10x the length, in other words, you basically create a bigger transistor, you have more charge carriers that get to traverse the channel, and you get more current, right? Now, remember that in digital systems, the voltage is basically fixed, VDD, right? So if you're getting more current with a fixed voltage, what that really means is your on resistance is lower. Basically, you're lowering the on resistance of the transistor. So when the transistor is on, it can transmit more current from source to drain, right? Now you might say, well, why would you want to do that? Why would you want more current? It makes the transistor more powerful. It makes it have a higher drive strength. And it can drive in other words, it has a lower resistance. And remember, the time is all based on just the resistance times the capacitance, right? It's the RC delay. So if your resistance is lower, the transistor it switches faster. It's faster, right? So you can adjust the width. So as I mentioned, typically the minimum width is about 10 times the length. So if you have a 4 nanometer transistor, the length is 4 nanometers, the width is 40 nanometers, right? But as a designer, you can increase the width, and often designers will do that. So they always keep the length minimum, always. You never make the length non-minimal. This always has to be the minimum feature size that the photolithography process will allow. But the width, you can deliberately make the width bigger. And basically, the bigger the width, the more powerful your transistor is. The faster it'll switch, the lower on resistance it has, right? So generally speaking, the width is in multiples of the minimum. So you can have a size 1 transistor or a size 2 transistor, which would be 20 times, where the width is 20 times that of the length, or a size 4 transistor. And typically, in a standard cell library, like you'll go to TSMC and they'll give you the technology, you have to sign the NDA, they give you the technology library, you fire up Cadence, and when you put your transistors down or even your gates down, you can choose size. You can say, oh, I want a double size inverter, please. Boom, put down a double size inverter. It has double size transistors, and by size, I mean width, not length. The length is always minimum, width can be bigger, okay? So that leads me to this RC delay model. So this is a way to estimate the speed. So as I mentioned, NMOS has, so there's K, which is the size. Again, width, okay? So if you increase the size, you reduce the resistance, right? So the resistance is R divided by K. If you increase the size by a factor of 2 and you make a double-sized transistor, you get half the resistance, right? That's pretty cool. But there's a price to be paid for that. Because if you make the width twice as big as the minimum size, the area of the capacitor is also doubled. So now you have double the capacitance as well. So you get more current, you get less resistance, but you get more capacitance, which means that you have a more powerful gate in terms of its output, but it's going to take more to turn on that gate because he's going to have a higher input capacitance, right? So I've got a bigger amplifier, but I need a stronger input signal to drive that amplifier, basically, right? And not only that, but check this out. Not only does the area of the capacitor that forms the gate twice as big, but guess what? The diffusion areas are twice as big too, because the diffusion areas are sort of, you can see these diffusion areas are matched to the width as well. So the gate has a width, but the diffusion areas get the same width. So now the reverse biased diode formed between the diffusion areas and the substrate is also doubled. So you get a double whammy. You get twice the capacitance on the gate, which is the input of your logic gate, right? And you get twice the capacitance in the diffusion areas, which is the output of the logic gate. So you get burned twice for that extra power, that lower resistance. The resistance is the drive strength. You lower the resistance, you increase your drive strength, but you add more capacitance internally. Okay, so what that means is that the NMOS has a resistance of R divided by K, where K is just the size, right? The gate has KC, where C is the unit capacitance, K is the multiplier. So KC, if you have a double-sized capacitor, double-sized transistor, you get double the gate capacitance. And then both the source and the drain also have KC capacitance, right? Now you might be saying, wait, are you telling me that the capacitance of the gate is C, and that's exactly the same as the reverse biased diodes in the diffusion areas? Yeah, it's about the same. It's not exactly, but it's close enough to same amount of capacitance. Gate capacitance, diffusion area capacitance, the same, right? So you're dividing by K for the resistance, but you're multiplying by K for the capacitance. And then this is the NMOS, and this is the PMOS, same thing. Now, the only saving grace, though, here is that remember that I mentioned something here. Remember there's the capacitance, capacitors have two terminals. If you look at this PMOS, remember the PMOS is the pull-up network, right? Which means that one of the terminals is connected to VDD, right? So the source is connected to VDD because that's how you pull up the output of the inverter, right? But the capacitor, remember that the PMOS substrate is going to be connected to VDD to get that negative voltage on the gate when you put a 0 in. Substrate's also VDD, right? Which means I've got VDD here and VDD here, which means I have a capacitor, but both sides are connected to VDD, so I don't care. It doesn't do anything. It doesn't hurt me because it's not a very good capacitor when both sides are connected to VDD. However, the other side, though, is a problem, right? Which is the source, or the drain, actually. Yeah, this is the source. The source is the top and the drain is the bottom on the PMOS. I don't know why they have it swapped with that one. But anyway, it doesn't matter because it's just convention. The source and drain are interchangeable here. But typically the source is VDD on PMOS and source is ground on NMOS, but it's not that important. Okay, so the point here is that only one of these guys actually hurts me, but that's only because it's an inverter. Once you get to more complex gates, then that changes, right? Does that all make sense? Does it make sense? So basically, what we're showing here is there's a switch, which is modeling the switching behavior of the transistor. When the switch is on, you got R, which is the on resistance of the transistor. Remember, on is how much resistance is seen between the source and drain when the transistor is on. Lower resistance means more power, higher drive strength, right? Then the capacitance, you got capacitance on the gate, and you got capacitance on both source and drain because those are diffusion areas and they're reverse bias diodes, right? Okay, so check this out. Let's say I have an inverter. I got an inverter. Oh, one other thing, I forgot to mention this. So PMOSs have to be twice as big as NMOSs to be balanced. Why is that? Because yes. The transistors are named after the diffusion areas, right? So a PMOS has P diffusion areas, right? Which means the minority charge carrier on a PMOS are holes, right? Because the substrate is N type, which is electrons, but the holes are the minority carriers that come in the channel, right? Holes have half the mobility of electrons. So in terms of carrying charge, Holes move at half the speed. Half the speed. Holes move at half the speed as electrons inside of a silicon lattice. Why is that? I have no idea. Some kind of chemistry, quantum mechanics thing. Holes have half the mobility of electrons. In order to make up for that, PMOSs are going to be twice as wide as NMOSs, okay, in your gates. Make sense? Okay, so that's why you've got a 2 here and a 2 here. These numbers are the sizes next to the transistors, right? You guys with me? Okay, so now I've got an inverter driving another inverter. And remember, we're talking about propagation delay. So we want to know how long it takes to propagate through this first inverter to get to the second inverter, right? So how do we measure that? Well, pretty much just add up all the capacitance and resistance, essentially. Pretty brain dead, right? You just say, how much capacitance do I have and how much resistance do I have? And you add it all up. Well, remember, you have to consider the state, though, right? So in this case, check this out. I am setting the input to 1. A is 1. What does that do? Pulls the output down, right? Because I'm inverting 1, I'm going to put out a 0, right? What does that mean? It means the NMOS is on, the PMOS is off, okay? Under this condition, this is what the equivalent circuit. Now, again, keep in mind, this is the NMOS resistance, that's the PMOS resistance. And remember, they're both R, even though this is size 2, because you have to size up the PMOS by a factor of 2 to get the same resistance as the NMOS, right? So it's kind of confusing, but that's how it is. You always have, PMOSs have to be twice the size because the holes are just weak mobility, has bad carriers, slow carriers, charge carriers. Okay, so I've got a resistor here and a resistor there, but guess what? That resistor doesn't matter because it's turned off, basically, right? So that top resistor, who cares? The PMOS is turned off, right? So I've got a capacitor here on the driving gate's diffusion area on the source, but I don't care because both sides of that capacitor are connected to ground. So I don't really care about that capacitor. But this one, this is the drain. The drain has a capacitor effectively on the output of the gate down to ground. So that's directly putting a capacitor on the output of the gate. Devastating for speed, right? You're basically putting a low-pass filter on the output of that gate, but just a consequence of transistors, no way around it. So this capacitor counts, this one doesn't. Now, this one also counts because even though this transistor is off, you're still connected to one side of it, and that side of it has a capacitor of VDD. So now I've got a capacitor from the output of the gate down to ground and from the output of the gate up to VDD. So I have double capacitors there, right? Then on the input inverter, now I got gate capacitors on that guy. So this is the input capacitance of the downstream inverter, the gate I'm driving, the gate I'm sending my output to. This is C and 2C. Why C and 2C? Because remember, I'm driving an inverter. An inverter has 2 transistors, a P and an N. I got to drive both their gates. Both their gates are capacitors, right? CMOS gates have 2 transistors for each input. So 1 input on an inverter, 2 transistors, double the capacitance. So that's, actually it's triple the capacitance because remember the NMOSs have to be twice as big. I'm sorry, the PMOSs have to be twice as big. Sorry, they pull up. Okay, so now if you take this circuit and you simplify it, we're going to simplify this. We're going to get rid of this guy because it's a capacitor that's got ground on both sides. Get rid of this guy, keep this guy, keep this guy, get rid of this guy because the transistor's off, so I don't care. He's disconnected, right? Keep this guy and keep this guy. So what am I left with? How do I add all these up? Well, pretty much resistance is just R, right? Because this is a size 1. R. Capacitance is C plus 2C plus C plus 2C, which is 6C, right? So the delay of this guy is R times 6C. Now you might say, wait, well, hold on a minute. You're telling me that ohms times farads is seconds? Yeah, weird. Units are weird, right? Ohms times farads is seconds. This is seconds. This is literally seconds, right? You might say, well, it's got to be small seconds, right? We're talking picoseconds here. Yeah, but we're talking picofarads too, right? We're talking ohms and picofarads, picoseconds, right? But that's the propagation delay, but for pulling down. That's assuming that that's the propagation, that's the falling propagation. Remember, we didn't differentiate falling and rising before. Now we have to differentiate them. This is falling propagation delay. Of course, you'd have to do the same thing on the high side to get the rising propagation delay. Okay, so what happens then if the inverter was not driving one inverter, but was driving 4 inverters? One inverter, output fanned out to 4 inverters. This is called the FO4 gate delay. This is a common way to characterize technology. Like when Intel comes out with a new technology, like we got the 4 nanometers. It's like that, yeah, that's great, but what's your FO4 delay? I don't care about 4 nanometers. I care about how fast the friggin' inverter is, because that's your basic delay. That's your basic gate, right? How fast is it in seconds, Intel, right? So this is the FO4 delay. And you can calculate the FO4 delay if, of course, you know what that capacitance and unit resistance is. So in this case, this is again, this is pull down. So everything is the same as the previous example. The only difference is that all the gates are the size the same, but because I'm driving 4 inverters, I have one inverter that's sending its output to 4 copies, 4 inverters. The only thing you have to adjust as compared to the last example, is the gate capacitance on the output, because I'm just driving 4 gates now. Well, actually 8 gates, because each inverter has 2 transistors, and there's 4 of them, and 2 times 4 is 8. Yeah, so I'm driving 4 of these gates, right? So basically, now it's R times C times 15, right? So obviously, it's slower. Okay, now here's where things get a little crazy. How about a NAND gate, though? What if I don't have an inverter? I have a NAND gate. Well, now things are a little harder, because now I have transistors connected in series and parallel. But the series is the hard part. The series is the one that's a little harder to figure out. How do you figure out? Because you can't just add R and C when you have series transistors. Okay, so basically, the way you do it is you use a technique called Elmore delay. So Elmore delay is when you model the pull down or the pull up network as an RC ladder, meaning that you have a circuit that looks like this. You have a voltage that's coming in, and you've got a resistor and a capacitor. So yeah, just R times C. But there's another resistor after that one, and then another resistor after that one. So you end up with this is called a lumped, this is basically a transmission line model is what it is. They call this a lumped model. Every R and C is a lump, right? But it's also applied to transistor networks for pull-up and pull-down networks as well, right? So why would we use this? Well, this is used, well, basically for like a NAND gate where you have, or an OR gate, right? Where you have, it's for this. When you have these guys connected in series, right? You got 3 transistors in series, and you have to calculate the pull-down propagation delay, right? So how do you do that? Well, you use this. Elmore delay is very simple. It's basically just R1, you just take the first RC, right? Then you add R1 plus R2 times C2, right? Why? because R1 and R2 are connected in series. So this is a series resistance charging or discharging this capacitor, right? So you have one resistor taking care of this first capacitor, but you have two resistors taking care of this capacitor, and three resistors taking care of that capacitor, right? So it's basically, it's R1 times C1 plus R1 plus R2 times C2 plus R1 plus R2 plus R3 times C3, right? So you just tally up the delay through the RC ladder, right? Okay, so here's an example. This is pretty neat because you can look at, so in this case, you can start looking at the difference between propagation delay and contamination delay. So in this case, what is the worst case rising and falling delay of a 3-input NAND driving H identical gates? Right? Now you might say, what do you mean 3 identical gates? I mean, AND has 3 inputs and only 1 output. So how could the 1 output? Well, what this means is the 1 output is driving one input each of H identical NAND gates, right? Is the idea. Okay, so so in this case, if my input is, so if I want to look at the rising delay, okay, let's say my input is, this is where input becomes important. So remember that a NAND gate is basically always going to give you a 1 as the output unless all the inputs are 1, right? Because it's the opposite of an AND gate, right? So let's say that only one of the inputs is a 0, and the other two inputs are 1. So this is going to give me, this is going to pull up, right? So what that means is that this is a little confusing, but the thing is here is that there's 3 gates that are in the pull-up network. But if I put an input of 0, 1, 1, what I'm basically doing is just turning on one of these 3 guys, right? Okay? Now, that's kind of the worst case scenario for pulling up. Why? Because if I turned on multiple of these gates are connected in parallel, right? And you guys know from circuits class, if you have parallel resistances, you get less resistance, right? And resistance is speed, right? However, there are 3 parallel resistors here, right? But my input to the NAND gate is 0, 1, 1, which means only one of them is going to get used. Only one of them is activated and the other 2 are off, which means this is bad because I had the ability to get 3 parallel transistors up to VDD, but because the user only gave me 0, 1, 1, it's only turning on one of them. So my pull-up resistance is only R. It could have been R over 3 if I had all 3 of those guys on, but it's only R because I only get the benefit of one of those pull-up resistors that are in parallel, right? Because that's a bad input. That's a bad input for delay. Now, think about this. If I had 0, 0, 0 as my input, that's a better input because then I get more drive strength. I get a faster, in this, what I'm describing is the contamination delay, propagation delay difference, right? So because I'm giving it the worst possible input, I'm going to get the propagation delay, not the contamination delay. And this again is for the pull-up. So I've got one pull-up resistor here, right? Meanwhile, I've got 2 pull-down resistors, but all 3 of them have to be on to pull down. But I still have 2 of them on, right? Because again, 0, 1, 1 means 2 of my NMOSs are on. So I don't fully get to pull down. The circuit gets interrupted before I get to pull the output down. But you still got to consider the effect that has potentially on capacitance, right? Because I've got 2 of the 3 pull down guys on. Okay, so anyway, what ends up happening there is the inputs, so basically what Y sees here, so if you look up here, if you look at the inputs capacitance, it's 9 plus 5H is the total input capacitance seen at Y, right? Actually, this is input plus this is also the drain capacitance of this guy, right? And then 2 of these guys are on, and actually these guys actually don't contribute anything, right? Yeah, this guy doesn't. The only thing I care about is this right here. The only thing I care about is the pull-up resistor plus whatever seen at the output, Y, right? So actually these guys are not relevant, even though 2 of them are on. Just the PMOS is relevant to the delay, right? And which also means there's no Elmore delay here because I don't have a ladder here because there's just there's just basically one resistor up to VDD, that's it. There's no RC ladder, right? Very simple. However, if I'm pulling down, so let's say my input is 111, well, that's the only case for an AND gate to actually pull down, right? So now I have an RC ladder because all three of these pull down NMOSs are now on, so I've got three NMOSs in series, right? So now I have to do that trick where you apply the Elmore delay. So it's basically the capacitance. In this case, oh, by the way, these guys, for some reason, I got this example from the book. For some reason, they put the size 3 on these pull down. See that? So that's why it's R over 3 here. So it's R, this is C times R plus 3C, this is the next one, plus R over 3 plus R over 3. So R over 3 plus R over 3 is the series resistance of these first two transistors. And then once you get to the last one, you have series resistance of 3 transistors plus the, actually, I'm sorry, I went the wrong way. This is the bottom one, this is the middle one, and this is the output one right here, right? Yeah. So this is the final, so this 9 plus 5H times C is the output capacitance, right, of the gate, of the output. So basically what's happening here is I went the opposite way. You start at ground, right? I was starting with the output and working down. I should have started with ground. You start with ground and you work your way up. So here's ground. I go through the first resistor, which is R over 3, right? And then I add its capacitance. What's the capacitance? Well, that's the drain capacitance, right? So that's 3C, right? Then I go through, from the ground, I go through 1, 2 resistors, so that's R over 3 plus R over 3. Then I multiply that by 3C, that's again the drain capacitance. And then I go through the third, which is basically the last transistor before I get to the output. And that's going to be R over 3 plus R over 3 plus R over 3. And then I'm going to add the combination of its diffusion resistance, its drain capacitance rather, plus the input capacitance of the downstream gates, right, which is giant, right? It's 9 plus 5H C, right? Okay, so that's basically worst case scenario, propagation delay. But notice I still have to figure out, like when I'm calculating propagation delay, I either have to separate it into rising and falling propagation delay, or I have to take whichever one of these is more and just call that the propagation delay. I think that's generally what's done, right? So I think in this case, what's the bigger number? 9 plus 5H RC or 12 plus 5H RC? Obviously it's the 12, right? So the overall propagation delay is actually the falling propagation delay because of this stupid 3 transistors in series to make this NAND gate, right? Now you can imagine, by the way, in real chips, you're never going to see a single gate with more than 4 or so inputs, right? This is the problem, is you get hammered once you start putting all these transistors in series. You know what I mean? So you're not going to see like a 20 input AND gate or a NAND gate. You don't get that. The cell libraries you get from your fab are always going to have relatively few number of inputs. If you need more inputs, then you just create multiple gates. You just chain together multiple gates to create a bigger logic circuit. You guys with me? Right? So in other words, there's basically, I think when I used to do this back in grad school, it was basically 3 inputs was the max. You'd never see a gate with more than 3 inputs, unless it was like a or I, A or, there's kind of special gates that are not, what's it called? A or invert gate, A or invert, which is kind of a complex gate. And I think those ones might have 4 inputs. But anyway, generally speaking, 3, 4 inputs is the most you're going to find because of this crazy capacitance you get when you have all these transistors in series. And this is with, by the way, this is with making notice that the NANDs are bigger than the NMOSs are bigger than the PMOSs. This was done deliberately. We want to make these guys stronger because of all the ones that are in series here, right? That's why these guys are 3. Okay, anyway, so but then contamination delay is where you can look at best case scenario. So as I mentioned, if your input is 0, 0, 0, then you've got 3 parallel resistors in your pull-up network, right? So you actually get really good drive strength pulling up if you set all inputs to 0, 0, 0, because you get the benefit of having essentially a triple transistor pulling up, because it's essentially 3 transistors in parallel, right? So that would be a contamination delay. Okay, any questions about that? Okay, that's all I have for CMOS. CMOS design. Okay, so I mentioned the final exam is on Monday, and I have some review questions here. The final exam is comprehensive. It'll be 2 hours long. And I'm going to emphasize the material that I covered since the midterm, the conceptual stuff. But you can still expect to see some stuff on there from the beginning of the semester. So make sure that you go back over your midterm exam and the quizzes and stuff from earlier. So here's an example question I might add that kind of combines together stuff from both halves of the semester. So this one says, consider, well, the first part of this is just purely the first part. Consider the risk 5 design below. Is it possible to add support for an add with right logical shift? What does that mean? It means you're adding 2 registers, but before you add, you shift the contents of the second register. Why would you do this? Can anyone think of a reason why you'd want to do that? So this is a proposed new instruction that's an add instruction, but instead of just adding 2 operand values, it will first shift the second operand by a shift amount that's given in the instruction. By the way, the ARM processor has this. That's where I got this idea from. Any reason, any idea why you'd want to do that? Well, you guys remember the fixed point stuff that we did earlier, where, remember, when you multiply 2 fixed point numbers, the number of fractional bits increases as compared to the inputs, right? Remember that? So if you multiply 2 numbers with 4 fractional bits, the result will have 8 fractional bits, right? But then if you want to accumulate that, right, let's say you do that, now I want to add that value to a sum that has 4 fractional bits. Well, you can't do that because you can't add a number with 4 fractional bits with a number with 8 fractional bits. You have to line up the decimal points first, right? You have to make the number of fractional bits consistent before you add or subtract, right? That's why floating point is so slow. Like when you add floating point numbers have, they have a floating decimal point, right? So when you add 2 floating point numbers, you have to denormalize one of them before you can add them. And that denormalization is what takes all the time. That's why floating point is so expensive. That's why people don't use floating point for machine learning often, because that denormalization is a pain, costly, right? Well, that's basically what this instruction would do, is it would basically assume that the second operand has had its decimal point shifted already from a multiply. So this would basically allow you to fix that before you add, and you can handle this all in one instruction, right? This is pretty cool. That's why ARM has it, right? Otherwise, if you're in RISC-V, you got to have a whole new instruction to do that, right? So the question is it possible to add support for that in our processor? Now, never mind the fact that there's no actual RISC-V instruction that does that, and if you added support, you would no longer be in spec, right, for RISC-V. Although RISC-V does have custom instructions, but that's another story. Anyway, is it possible to do that? Is it possible? Sure, it's possible. But you'd have to add some hardware. In fact, you'd have to add a shifter, right? So my answer says not possible without adding a second ALU or a dedicated shifter to shift the B input into before sending it to the primary ALU, right? Make sense? Now that's, of course, assuming we're pipelining. You could also make this multi-cycle where you basically stall. If you get this instruction, you stall, and then you reuse your ALU twice. But then you might as well just have 2 instructions, right? If you're going to do that. Sorry? Yeah, sure, absolutely. Yeah, if you said I can make it multi-cycle, or I can add another shifter, or I can add another ALU. Yeah, you'd have to add an ALU if you wanted to keep the pipeline moving, basically, right? Okay, so that's the answer. So that's an easy one, but the next one's a little harder. Using the delays in the table below, what's the minimum clock cycle time for the processor design? So now I'm giving you the propagation delays for all of the stuff in here, including the register propagation delay, right? That's the PCQ, PPQ, PPD, PQD. I can't remember what the variable is for that, but basically how long it takes for a register to update after the clock, right? Okay, so how do you figure this out? Well, this is actually tricky because there's a lot of paths, there's a lot of data. Your CPU was simple, but it still had a lot of data paths in it, right? So I'm going to just show you quickly because this takes some thought, right? Okay, so in the fetch stage, you have two paths. You have basically the PC plus 1, right? So that would be 10 picoseconds to update the PC, 20 picoseconds to add 1 to it, and then you have to add the setup time back into the PC, right? You guys remember that? PC just adds 1 and loops back to the PC, right? It's an incrementer, right? But in order to make an incrementer, you have to consider the register delay, the adder delay, and the setup time, right? But you also have, this is the real problem, is that you have the PC, then it goes into the instruction memory and spits out the instruction. That's the real problem, right? You have to read an instruction memory. So in this case, based on the numbers I gave you, reading the instruction was way slower than incrementing the PC, 260 picoseconds. Then in the execute stage, now keep in mind, all these are going on in parallel, right? So you have to calculate all these paths and just find out what the maximum one is, right? Because they're all going on at the same time. So while that's happening in the execute stage, you got to read registers from the register file. You have to go through the ALU mux. Why? Well, because there's a mux there, right? This guy, right? Read registers, go through mux, go into ALU, right? Then go in, then setup time. That's 250 picoseconds. Then there's the LUI pipeline register setup, which is real fast. Then you've got control unit decoding the instruction and sending the output of the control unit into a register, so that's 125. Then the write back stage, you have register propagate. Register propagate, again, is just the register delay, the propagation delay of the register. Mux, which mux? Well, the write back mux, this mux here, right? Register, mux, back to register file write, right? 45 picosecond. Anyway, turns out the highest delay here is reading the instruction. 260 picoseconds, which is, if you take the reciprocal of that, it's 3.8462 gigahertz. All right? Now, I don't know. These are made up numbers. I don't know. You know, I don't really know where the critical path is in our course CPU, because I had several students look at that in the timing analyzer, and they all came up with different answers. Alex did it. Soyash did it. Soyash got it, his critical path in the branch resolution logic. And Alex was had some weird thing where he was using synchronous resets for the registers, and that was causing all the delay. So anyway, each of you may have different critical paths depending on how you design your CPU. Okay, so choose which of the delays to reduce by 20%. And I said need to reduce the memory read. Again, for the instruction read. What would happen if the reg cell was stuck at 0? Okay, we already talked about that. Blah, 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 blah. Okay. All right, so moving along. This one is pretty cool. This is the same design basically, but in this case, I have this question. You guys remember this question from the midterm, but this one has a twist. This one has an add-I, an add-I, and a branch, right? And then I say, what cycle do each of these fetch, execute, and decode in? The tricky part here is that the branch, so basically this first instruction initializes register X2 to 2. The second instruction decrements X2. And the third instruction checks to see if X2 is 0, and if not, it branches. And the branch offset is -1. And remember, I told you that -1 means go up one instruction, right? If this were MIPS, -1 means branch to yourself. But in RISC-V, -1 means go up 1 because of the way they calculate the branch offsets. Okay, so anyway, so the cool thing here is, this always kind of gets me to, okay, so when the branch is in execute is where we're going to resolve. So you can't fetch the second instruction until the cycle after the branch was in execute, right? So in cycle 3, the branch was executing. In cycle 4, we fetch the target, right? Is that right? Yes. Yeah, because you'd end up with a bubble there. Because essentially in cycle 4, notice there's nothing in the execute stage in cycle 4, right? Cycle 4, I've got fetch, I got an instruction in fetch, and I got an instruction in write back. You see that? There's nothing in execute. What's in execute? Well, it's a bubble, it's a stall. It's the stall from the branch. When you get a branch, the next instruction after the branch is a stall. It's a no-op. So that's why cycle 4, you don't see anything, you don't see an E, right? Okay, well anyway, that part is kind of complicated. That's actually, well, I think in this case I gave you that, and then I just asked you what the signals were. So obviously when the branch is in execute, the stall fetch is 1, but the stall execute isn't 1 until the following cycle. Remember, the stall execute is a delayed version of stall fetch. Okay. Anyway, basically when stall EX is 1, that means nothing's in, effectively no instruction is in execute, right? You guys remember that from your lab. Okay, yeah, so a couple other questions about that. Okay, then we have sequential logic. What's the difference between combinational and sequential? Combinational is a function of inputs. Sequential is a function of the inputs and the input history. What's the difference between a D-latch, D-flip-flop? Latch is level sensitive, flip-flop is edge sensitive. Consider the circuit below. What's the next state logic? Okay, remember to solve this one, you basically have to figure out what the prime, Q0 prime, right? In other words, you got to figure out what the Boolean logic is for the D input on each of the flip-flops, the registers, right? So you have to trace back. So what is this? Well, it's the and, it's A and something, A and Q0 or Q1, right? So you got to just basically trace the wires there. Okay, then fill in the timing diagram below. So once you have the next state logic, you can figure out, how the state evolves based on both the input and the current state. Using the technology, can this circuit operate at 2 gigahertz? Okay, so in this case, I give you the propagation delay of each of the gates and the contamination delay of each of the gates. And I give you TCCQ, contamination delay of the flip-flops, TPCQ, that's what I was trying to think of, PCQ. PCQ is the propagation delay of the flip-flops. Setup time, 100 picoseconds, hold time, 20 picoseconds, clock skew, 10 picoseconds. And all you have to do is plug these into the equations that I gave you to figure out if it works. So in this case, it turns out that the setup and the hold constraints for both Q0 and Q1 check out. So the answer is yes. Okay. Now notice though, I have to do this separately though for Q0 and Q1 because you basically have to do you have to do an analysis, a setup and hold time analysis for each of the 2 registers in there, 2 flip-flops. I don't think we ever had an example like that before. Consider the circuit below. Is it a valid sequential circuit? No, because it's combinational logic has a loop back and you don't want that. Technically, I think the terminology is actually wrong here. I should have said, is it a valid synchronous sequential logic circuit? But anyway, in general, you don't want to have any loops in combinational logic, right? It makes it asynchronous, right, essentially. Consider the following FSM design. Assume the state variable is named S1, S0. And then the question is, what's the truth table for the next state logic? So next state logic is basically it's determined from the states and then the transition. So you see from 0, 0, 0, 0, right. 0, 0 means these two rows, right? So these first two rows of the truth table basically just deal with the transitions out of the state, right? Does it make sense? Because the state encoding is 0, 0, right? So these first two rows are, I'm starting from 0, 0, and then there's also A, right? Input A, right? That's why there's two rows. So there's one state, 0, 0, but A can be 0 or 1. And based on that, I can decide which state I'm going to, which is the next, S. So I'm either looping back to 0, 0, or I'm going to 0, 1. So that's this. I'm either looping back, so that's these two transitions, right? So the first two rows of the truth table are just basically that transition and that transition. Okay, write a truth table for the output logic. Again, that's pretty simple because you just have to look at basically, you can tell, just looking at this, is that the output logic is S1 and S0, right? Because the only time the output logic is 1 is when the state is 1, 1, right? So it's just an AND gate, right? Yeah. And then fill in the state row. Whoops, sorry. Fill in the state row here in the timing diagram. And in this case, you can see you start with 0, 0, and based on A, you're going to transition to different states. Okay, and then it says sketch the state machine diagram in the system Verilog. Notice I've got the type def enum for state type. This is the clocked logic that just takes care of putting next state in a current state and resetting. And then this always com is the next state logic, which comes straight from your next state logic that we figured out earlier. And then this assign is the output logic, which again is just the AND gate. No, it's not. Is Y? I thought it was AND. Yeah. Well, that's not right. It says assign Y current state S1 or current state. Oh, I'm sorry. That was because, sorry. This code is for this design, this state machine. Sorry. Not the one above. It's this one. Right. It's a different one. Same idea though. Yeah, so basically write system Verilog for this state machine. Okay, here's another state machine. And this one asks, give a Boolean expression for F. F is the output. Pretty much F is just, F is here. F is basically always 0 except for this got all state. And got all is 1, 1. So this is, again, just an AND gate, right? Okay, this is another timing analysis question. I'm running out of time, so I'm going to go kind of fast here. This is just asking to do setup and hold time. This is another one. This is asking what the propagation delay is and the contamination delay. This one's a little, this one's actually not tricky because there's no fan-outs here, so it's very easy to find the paths. When you have fan-outs, right, when you have wires that branch off and go to multiple places, the number of paths increases exponentially when that happens, right? But there's no fan-out, so you basically just have one path from each input to output, right? So A, B, C, D, E, A, B, C, D, E is just 5, there's just 5 paths, right? And each one of those paths, some of them are the same though, right? So D and E are going to have the same timing. A and B will have the same timing. So you really just have 3 different delays. And most likely the critical path delay is going to be A, B to Y, right? Because it goes through 3 gates. Now, keep in mind though, I could ask you a trick question. I could have a case where you have A and B going through 3 gates, but that might actually be faster than this path going through 2 gates because, for example, this OR gate might be super slow, right? It's not the number of gates, you have to consider how fast each gate is. You guys with me? Right? So if this OR gate had a very high propagation delay, then D and E to Y might actually be the critical path. But it's usually it's the number of gates you go through is the most number of gates you have to go through. Okay, then consider the K-map with marked groupings below. You have to remember 211. You guys remember K-maps, right? Carnot maps. So the question is, can this circuit potentially glitch when a single input value is changed? Can you get a glitch? Yes, you can glitch. if you go from this K-map grouping to this K-map grouping, what would that involve? That would involve going from, say, that cell to that cell. So what are you changing? A, right? A is the only thing that changes. A goes from 1 to 0 if you go from that cell to that cell. Make sense? That might cause a glitch. Might cause a glitch, right? If you want to make sure it doesn't cause a glitch, you have to cover it. You have to cover that transition, which means you have to add another K-map group that goes all across this row. Yes? So glitch is when you change an input, and because of fan-outs in the circuit, this only happens if you have fan-outs. What ends up happening is that one input has different paths to the circuit. One of them is a long path, and one of them is a short path. And so you change that input, and the short path completes first, right? And then you get an output, right? And then the long path finally catches up to it and finishes, and you get another output potentially. That's a glitch. That's basically when you change an input and the output of the circuit changes multiple times. It should settle, it will settle by whatever the propagation delay is. But there's a period of time between the contamination delay, which is the shortest path of the circuit, and the propagation delay, which is the longest path of the circuit. In that middle time, between those two delays, you can get a glitch, right? It's just the difference in timing through the circuit. But again, that would never happen in a circuit like this. This circuit, it can't happen in this circuit because there's no fan-outs, right? There's no way that one input can have two different times getting through the circuit, right? Because there's only one path from each input to output, right? So that can't happen. You can't have a glitch in this circuit. But if you had a fan-out, right? If you had branches, if you had one input that branches and then goes another way through the circuit, right? Which is very common, right? This type of circuit with no fan-outs is actually uncommon, right? Very simple. But if you have fan-outs in the circuit, then yeah, you can have different you can have one input that takes different amounts of time to work its way through the circuit, to trickle to propagate through the circuit. That's what a glitch is, right? Okay, usually not harmful though, but it looks goofy when you see that glitch on your simulation or your oscilloscope. All right. Now this question, let's see, what is the propagation delay of the circuit? The issue here is that, the problem with this is that I don't give you I don't give you NAND, right? There's a NAND. You see that NAND? There's a NAND gate here, but there's no NAND gate in the table, right? That's the problem. So I don't remember if I intentionally did that. This is from an old exam. I don't remember if I intentionally did that or if that was a mistake on my part. But basically what it meant is the question, in order to answer the question, you had to figure out how you were going to reconcile that. So either you convert the two-input NAND gate into a two-input AND gate followed by a NOT gate, or you convert the two-input NAND gate into NOT gates feeding a two-input OR gate. So this is what I'm talking about here is De Morgan's law, basically. If you guys remember De Morgan's law from 211, I'm using De Morgan's law to figure this out. But there's different propagation delays depending on how you do it. Okay, and the contamination delay, and then, blah, 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 digital building blocks. Okay, real quick, I only have a minute left. Give a Boolean expression for the carry-in input for column 3 of the following types of adders. Ripple carry adder, very simple. The carry-in into column 3 depends on the carry-in of the column 2. The carry-in of the column 2 depends on the carry-in of the column 1, right? So obviously there's 3 equations there. Carry look-ahead adder, it's generate and propagate, same kind of idea. And then write a schematic for a 32-bit comparator that takes blah, 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 and then it's essentially just a subtractor. Okay, and how many gate delays are needed for a shifter that performs an arithmetic light shift by 4? 0. 0, because if the shift amount is a constant, then it's just bit twiddling. There's no actual delay. The problem is when the shift amount is variable. That's a problem, because then you end up having to create a barrel shifter which has a quadratic cost, right? Or you can make a shift register if you're willing to you're willing to gradually shift it cycle by cycle. Fill in the Boolean equations for a 4-bit prefix adder. That just comes straight from the slides. And I think that's it. Okay, so yeah, there you go. Any questions? I didn't review the CMOS stuff because we just got done talking about it, obviously. But make sure you review timing analysis, digital building blocks, sequential logic, CMOS design. Yes? Yes. Yep. Okay. Make sure you remember your power, the static and dynamic power, static power. Yeah. About it. Any other questions? Okay, we'll see you in the lab and also then see you also in the final on Monday. Okay? You'll be here, yeah. Thank you. 4 o'clock to 6 o'clock.